So let me start by telling a little bit about myself. So my name is Anuj Pathania. I'm an assistant professor here at University of Amsterdam, and I started here a little more than 5 years ago. I am originally from New Delhi, India, and I did my PhD from Karlsruhe Institute of Technology in Germany. And my area of expertise is low power design, embedded systems, and electronic design automations or EDA. So today I'm going to talk about how to model the mean time to failure for multi-core processors that are resistant to core failure, which basically means that they can still survive if one of the cores or many of its cores still dies out and so on. So this is how a typical multi-core processor looks like. So you have a series of cores, and each core has its own individual memory, and and then these cores communicate using a shared memory, which is shared by one or more cores. And then the communication happens over a bus interface, and then the whole chip itself, the multi-core chip, communicates with other chiplets or other components using a off-chip component interconnect. So the idea behind core failure and resistant multi-core is that the the cores, they are allowed to fail. So generally, if a core fails at runtime for a normal multi-core processor, then the whole chip itself dies because the hardware and the firmware cannot handle a core not working properly. So either all the cores work, or if or the chip dies. But this technology, the core failure resistant, allows the chip to survive one or multiple core failures, and the cores which are still functional continues to work even if their fellow cores are no longer working. This technology is especially useful in server scenarios where cores are constantly operating at very high utilization, and there's also a lot of heat that is being generated, and because of the temperature, the core failure is very common. Some of these multi-core processors also have the ability to handle the failure of memory banks, for example, in the last level cache. But this is something which we have not explored yet. So here we will focus on mostly on the failure of the cores themselves, not the impact of what would happen when the memory banks start to fail and so on. So for this work, we took uh, applications which were given in form of a directed acyclic graph or a DAG, and then this DAG is scheduled to be executed on a multi-core processor, and then, for example, then the first core fails, then the whole system realigns itself, and the remaining cores must pick up the load of the first core failure and continue to provide the performance, but at a higher utilization, at a higher temperature, and so on. And then the process repeats till all the cores fail and there's no longer a surviving core. And because core failure is a random process, you have to simulate the whole failure of the cores, which would happen over many years. But in simulation, we do it kind of fast. You have to do Monte Carlo simulations several times to obtain the mean time to failure for this kind of processor. So, so here is a simple example where we have a dual core, core failure resistant multi-core, and there are two cores and they are working, and based on their initial working profile and what kind of workload they have experienced in their history and what kind of temperature the core have experienced, they have different level of reliability. So these reliabilities are generally measured in what we call the R value, when R value basically is a value between 0 and 1, which tells you that how likely it is that the core would fail in the next instant. So if an R value is 100%, then there is very little chance that the core will fail. Whereas if the core has a value of 0, then a value of 0, then that means that core is very old and could fail anytime. But let's say if it has a R value of 0.5, then basically it means that the core can, there's a 50% chance that in the next cycle the core would fail. Because core failing is a random process, but when we are doing simulations, we do not have real cores that are failing. So we basically assume that like if the R value drops below a certain value, then the core is dead, or we can assume that we run a random number generator and see if the number generator says, okay, the probability is higher that the core would fail, then we fail the core even if the R value is very high, and the core can similarly survive by the randomness even if the R value is low. So in this particular example, what we are seeing is that we have the reliability curve of a dual core processor, and one core has more aged age than the other core because it has a steeper the curve for the R reliability curve. So now the two things can happen in this multi-core processor. One thing is that in the next instance, when we are simulating, an older core fails first, or then on the other side, what could happen is that a younger core fails first just by the randomness simulations. So we have to cater for both of these cases. But but generally, what is assumed in most of the works or the reliability simulation is as soon as the first score fails, what would happen is the simulation stops and you report the time to failure. But in our case, that is not the case because we have the core failure resistance capabilities, which allows us to prevent the multi-core from completely dying. So we have to model the lifetime of such a chip. So this is how the fault distribution curve for the surviving core changes. So let's say in our case, the young core, the old core fails. So the core which is younger need to take over the load. So the reliability curve shifts for that particular core middle of its execution from the old red one to the new blue one. So if you want to model the curve for the whole lifetime of this chip, we have to create a hybrid curve where blue one was the time where there were two cores in the system, and the red one is now the time where there is one core in the system. So this is how the end eventual reliability curve for that surviving core would look like. And the curve will actually be much steeper because the workload has to be picked up, and that would mean that there would be more heat generated on this processor, which will accelerate its aging because it's not taking the full load of the system. And to do this, we created a framework called Slicer, which is a framework built on the Hot Sniper tool, which also George talked about with Hot Proton. So they are related. So basically, we used trace-based simulations in our Slicer framework based on this Hot Sniper tool, where we have a scheduler which reschedules the workload, and then we have thermal simulations, and then we have an aging simulator, and all of this work. And user provides with software description, hardware description, SLAs, and scheduling policy, and the framework can give you the mean time to failure. So what we did was that we didn't propose our own reliability scheduling algorithm. There are several reliability scheduling algorithms already out there. So we gave the same input in terms of this hardware software description and the deadlines, and we saw uh, the how good this reliability scheduling algorithms are. And our tools was able to say that, like, for example, this DWDS algorithm is much better at providing higher reliability within the same performance constraint than other ones in most of the cases for most of the benchmarks. So this is the final slide. And here I want to just give you quickly what things are happening. For example, what is happening. So in the first case, you could see that all the cores are active, and the tasks are relatively equally distributed. And then because the core one was more overloaded by the scheduler, it is the first one to die. And then what happens is that the tasks now are shifted more to the other cores, But the important point to note is that like even if a core dies, our simulation takes into account the fact that the core is still acting as a heat sink and can still survive, can still provide cooling effect to the neighboring cores, even though now it's not active. Especially now that it's not active and it's dead, it is in even a better heat sink than it was in the past case. So it would help the surviving cores a little bit with the temperature and so on, especially the neighboring cores. But eventually, because now the existing cores have to take more and more and more load, they start to become hotter and hotter, as you can see in the different steps, what is happening in the simulation. And eventually you reach a point that you don't have any more cores and the core failures becomes even more faster process because of the higher temperature and so on. And then when you simulate this hundreds and thousands of times, you can kind of get an estimation for the mean time to failure for core failure resistant multi-core chip. And with this, I would like to end, but I think the Q&A would be in the end. So I would hand back the floor back to Joe.